This is the fifth and final section of the methods in calculus chapter, and here we're going to be looking at integrating using partial fractions. Now you need to be careful with these questions because the question may not necessarily say use partial fractions. Sometimes it might tell you that, but often you have questions that look very similar to standard results, and if you're not careful you could easily end up using those standard results by mistake. So there might be a minus sign instead of a plus sign, or there may not be a square root where normally you'd expect a square root. So just be careful when you're doing these types of questions. Okay, so for this one we want to prove that integral 1 over a squared minus x squared gives you that result. Now if you're not careful, you might look in the formula book and say, aha, I can see that 1 over a squared plus x squared, if you integrate that, the formula book says that that gives you 1 over a arctan x over a plus c. And you'd be wrong, because this minus sign here makes all the difference, and it gives you a totally different result, and we're going to be using partial fractions to help us with this. Right, so the first thing, if I write this down, is that the bottom is the difference of two squares. So I have 1 over x or a minus x and a plus x. So let's do a plus x, a minus x dx. So we want to split this up into a partial fraction. So we want this a plus x, x, a minus x in the form a over a plus x plus b over a minus x. So you can see if you use that standard result, you'd be doing something completely different. So that means that 1 is equal to, or equivalent to, a times a minus x plus b times by a plus x. So let's make x equal to a. So this is unusual because normally we're making like x equal to a number, but in this case we've got letters in the denominator. So if we make x equal to a, we'll have 1 equals or is equivalent to, now this will disappear, this will become 2a. So I'll have 1 equals 2ab, which means b equals to 1 over 2a. Now if we let or x equal to negative a, then what will happen is this will go, so I'll have a minus negative a, so it becomes 2a again. So I will have 1 is equal to again 2a, so that would mean that a equals 1 over 2a, so we get the same values for a and b. So the integral now becomes, what did we have? I'm going to write it like this, 1 over 2a over a plus x plus 1 over 2a, a minus x. Now 1 over 2a is a constant, so it goes at the front now. So I will have 1 over a plus x plus 1 over a minus x Now what will happen, so I'll still have the 1 over 2a here, this will be log of the bottom log of this, because that differentiated will give you 1. So that first term will just give you log a plus x plus then the second one. Now what will happen is this differentiated is actually -1, so log of the bottom will give me a negative, so I need to cancel that out by putting a negative here. So I'll have log of a minus x, and then hopefully if we tidy that up we get the result that they want. So we've got the 1 over 2a there. So the log of something minus the log of something is the log of this divided by that. So log of a plus x divided by a minus x plus c, and we use the modulus sign, remember, because we can't do the log of a negative number. So if we just put the modulus sign in there, we get the result as required. Right, so on this equation we need to show that this integrated gives us these two terms here. So we're going to have to use partial fractions on this here, and we'll write it out. So 1 plus x over x cubed plus 9x dx, and we want that written as a partial fraction. So we'll have to factorize the bottom first. So we'll have x squared plus 9, so they're going to be the two denominators. So I want this written as something over the first factor plus something over the second factors. Now what I'm going to write at the top here may surprise you, because you may be thinking, well, I'll just do b there, and that's what you would normally expect to do. But actually what needs to be written at the top is bx plus c. Now I had to look this up. There is no reference in the Pure 2 book to partial fractions where you get a quadratic like that in a denominator. They do mention repeated factors, so if you had x over x plus 3 all squared, we know that we do b over x plus 3. Yeah, so you have your repeated factors, but this isn't a repeated factor, and there's no examples that show you how to do this. So first of all, this isn't a repeated factor. This isn't a repeated factor, and there is no mention of this type of partial fraction in the Pure Year 2 book. Yeah, and I had to look this up, and basically if you've got a quadratic in a denominator like this, we need to put an x in a numerator, because there could be an x in the numerator. It could be something x plus c. Yeah, so what we'll put down here is that if the denominator, I don't know if I said numerator a while ago, but I meant denominator. If the denominator is quadratic, okay, and not a repeated factor, then we must consider that there could be an x term in the numerator. Okay, so just be aware of that. If they do put a question like that, it would be a bit naughty if they did, because I can imagine students will just put a b at the top here, not a bx plus c, because this doesn't occur anywhere else in the Pure Year 2 book. So let's now deal with our partial fractions. Again, issues with spelling here. Partial fractions or partial fraction. So we want 1 plus x over x squared plus 9 in this form, a over x plus b x plus c over x squared plus 9. So from that, the numerators must be equal to 1 plus x. It's got to be equivalent to a times x squared plus 9 plus bx plus c times by x. Now, we can't solve this by choosing a value of x to make one side or the other disappear. I suppose we can if we chose x equal to 0. Yeah, let's do that. We can do that, but the rest we need to equate coefficients. So if we let x equal to 0, then we will get 1 on the left hand side is equal to 9a, which means a equals a ninth. But to find the other values of b and c, we have to equate coefficients. Yeah, because there's no other value of x that's going to make my other letters disappear. So let's say I equate coefficients of the x squared terms. So on the left hand side, as far as x squared is concerned, there's nothing, it's 0. On the right hand side here, I'm going to get a as a coefficient of x squared plus b as a coefficient of x squared when this gets multiplied out. So basically I've got a plus b equals 0. Now since I've got a is a ninth and a plus b is 0, it means that b is negative a ninth. So b is negative a ninth. So we need to equate some more coefficients to find c. Now that means equating the coefficients of the x terms. So on the left hand side, coefficient of the x term is 1. On the right hand side, the coefficient of the x term is just going to be c. So c equals 1. Okay, so we have our values of a, b and c, which can now go into our integral. So now we're going to be integrating this, so it's going to be 1/9 x, so 1/9 actually over x, because we might move things around in a minute. So 1/9 over x, that's the value of a, plus, now b was negative a ninth, so I've basically got negative a ninth x plus c, which is 1, over x squared plus 9 dx. Right, let's tidy up. So the first term, which is here, the ninth can go at the front, so that'd be 1/9 integral of 1 over x. Now we'll split this up, so we've got negative a ninth x over this plus 1 over that. So when we've got negative a ninth x over the x squared plus 9, actually means that we could bring the negative a ninth over to the other side of the integral sign, just leaving x over x squared plus 9. And then my last one, I suppose I should really put dx after each of these. So dx, and then minus dx minus. So I'm now taking out the last bit, so this will be not minus but plus 1 over x squared plus 9. So let's change that to a plus. So plus 1 over x squared plus 9 dx. Okay, so the first term here just became this, and then what I did, I split this fraction up. So I've now got 3 integrals, and I should be able to do each one. Now the first one, I can use log x for that one. The second bit here, I can do the log of the bottom with a little bit of an adjustment, because this is like f dash of x over f of x. And for this one, it's like 1 over a squared plus a squared. So this is going to be arctan. So what I'm going to do before I apply each integral, I'm just going to fiddle around with the constants in the second one, so that the top is exactly the bottom differentiated, f dash of x over f of x. Now for that to happen, I'll just leave a little bit of space for my constant in a minute. I want 2x at the top over x squared plus 9. Yeah, the bottom differentiated would give me, don't know why I keep putting x in, I did that before when I rubbed it out. Yeah, the bottom differentiate give me 2x. Now that means I want a half somewhere to make it balance, so I can put a half here, but I've already got a ninth here, so half times a ninth will give me negative 1 over 18. Okay, so that still balances out dx, and then plus. Now if I write the last one and just swap them around, so I've basically got 3 squared plus x squared dx, then you can see really clearly how I can use arctan to get my answer. Right, so here we go. First term, it'll be 1/9. That differentiated is log x, so 1/9 natural log x. Right, second one, second term here. Right, as I said, that fits the pattern where we've got f dash of x over f of x. So when we've got something like that, we know it's going to be log f of x. So it will be negative 1/18 in the right colour. So negative 1/18 of natural log of that denominator, x squared plus 9. And then the last part here, we can use arctan. So if I just write down as a reminder that if I've got 1 over a squared plus x squared, I want to integrate that, that becomes 1 over a arctan x over a. Now a I can see is 3 because I wrote 9 as 3 squared. So then the last part is going to be plus, and there's no sort of constants here, so it's just going to be plus 1 over a, so that's 1 over 3, 1/3 arctan x over 3 plus c. Now the last bit I need to do, I need to combine my two logs here, so I've got a division. But one thing you'll notice, they put all little things in here to catch us out. This says x squared at the top. Now that just says x. Now watch this. If I add an x squared here so that it fits, that means that this number here needs to be halved. So I've basically taken a 2 out of that, taken a 2 out of 1/9 and put it here. So if that's the case, this needs to be 1 over 18. Yeah, it's the same thing, but I've just made it try and fit. So now I can put these together. It's a division, and it's going to be 1 over 18 at the front. Okay, so that's the value of a here. Then log, natural log. Then I've got a division, and my division is going to be x squared divided by x squared plus 9, x squared over x squared plus 9. Suppose I don't need the modulus sign because it's x squared, it's always going to be positive, plus 1/3 arc tan x over 3 plus c. So it's quite a tricky question. There's all sorts of places where you could easily get caught out. There's the issue with this partial fraction here and putting the bx plus c at the top, which is new probably to pretty much most of you. Then there's this bit down here. Well, actually before that you've actually got 3 different integrations to do. You've got your log x here, you've got the log of x squared plus 9 here with a little bit of adjustment, and then we've got our arctan for this part here. Yeah. Then there's like the x squared, dealing with the x squared that's here, that could easily be missed. How can you get x squared? Well, by taking the 2 out and making the power and making this half the size. So I suppose we could finish it off by saying, well, our value of a is 1 over 18, and our value of b is 1/3, isn't it? So let's just highlight that. It's quite a tricky question, so you might want to sort of go over that and try it for yourself, watch it a couple of times just to make sure that you fully understand it. It's easy to get to slip up in that question. Right, first thing to notice on this question is that this is an improper fraction. Because it's an improper fraction, it means that there is a quotient, a whole number part, and we can get that whole number part out by equating coefficients, but I'm going to take that whole number part out by doing long division. So it's totally up to you whichever way you do it. So it means that I need to do x to the power 4 plus x. So let's make sure we stick zeros here. Plus x plus 0. And that needs to be divided by x to the power 4 plus 5x squared plus 6. So what do we get? Well, we're going to get the divisor goes into that once. So let's multiply the divisor by 1. Then we're going to divide or subtract. So when I subtract, what I'll have left is minus 5x squared plus x minus 6. So what does that tell me? That tells me that x to the power 4 plus x divided by x to the power 4 plus 5x squared plus 6 is equivalent to 1, that was my quotient, minus this, the remainder, over the divisor. Now, because I've got a couple of minuses there, I'm going to put the minus here and change the signs of these, okay, over my divisor. Right, so you'll remember from Pure 2 that now I do partial fractions on this part. So it's going to be 1 minus something. Right, so I want 5x squared minus x plus 6 over x to the power 4 plus 5x squared plus 6 equivalent to, right now I need to factorise the bottom. That factorises to x squared plus x squared. So it's going to be 3 and 2 that. So it's that I want written as a over. Now this is like the last example. This is going to be a quadratic in my numerator. So this needs to be ax plus b. So another one like the previous one where you haven't done one like that before with just a quadratic. And then plus cx plus d like that. So from there I can say that my numerator needs to be equivalent to ax plus b times by x squared plus 2 plus cx plus d times by x squared plus 3. So now we would we could choose values of x to try and make brackets disappear. Is that going to work? I don't think it is. No, so we've got to equate coefficients. Let me just write that. Right, so let me go through all the powers. Let's start with x to the power 4. Right, actually no, the biggest one's going to be x cubed, isn't it? So on the left hand side the coefficient's going to be 0. On the right hand side the coefficients of x cubed are going to be a and c. Okay, let's equate the coefficients of the x squared terms. So on the left hand side it's going to be 5. On the right hand side it's going to be b and d, b plus d. Right, let's now do the coefficients of the x terms. On the left hand side it's going to be -1. On the right hand side it's going to be 2a from the first bracket and 3c from the second bracket. That was the x terms. I don't know why I wrote x squared, that's the x terms. And then we'll equate the number terms. Now on the left hand side it's 6. On the right hand side it will be 2b plus 3d. Now I'm going to be real lazy and get my calculator to solve these simultaneously. So from the calculator I'll get a equals 1, b equals 9, c equals -1 and d equals -4. So if I now plug that in, that would actually give me, and I'll write that here, a is 1, so I'll have x plus 9 over x squared plus 3. And then since I've got a -1 and a -4, I'll put the negative at the front and write them as pluses. So I will get x plus 4, yeah, seeing that c and d were both negatives and I don't really want to put negatives there, over x squared plus 2. Now we haven't quite finished because the whole partial fraction was 1 minus that. So let's finish it off over here. So x to the power 4 plus x over x to the power 4 plus 5x squared plus 6 can be written as this: 1 minus, and it's going to be 1 minus all of this. So I suppose I could write it as 1 minus x plus 9 over x squared plus 3 and then plus, because I'm going to be minusing that negative, x plus 4 over x squared plus 2. So now we can move on to part B. So if we're going to integrate that, hence just means basically use your previous answer, don't start from scratch. We're going to split everything up. So we've got 1 we need to integrate. Then the next term, we're going to split up these fractions here into 2 bits, and the same here. So then I will get, it's not plus, it'll be a minus. So minus, and then we'll split that fraction up, so we got x over x squared plus 3 dx, and then it's going to be minusing the 9 over x squared plus 3, my arrows don't quite match up, dx, and then plus 4x over x squared plus 2 plus, that's dx, plus 4 over x squared plus 2 dx. So if you go for it term by term, the first term will just become x when it's integrated. The second one, where we'd probably want to put a 2x there, which means a half there, so it'll be log of the bottom, half log of the bottom, so minus half log x squared plus 3. Then if we look at the next one, we'll probably take the 9 over here, and this will be arctan, where a would be root 3, so I'll have negative, and then we'll have a 9 here, and arctan will be 1 over a, arctan x over a, so that's root 3, so that's the next one. Then this one here, again we would do log of the bottom, we'd want a 2x here, which means a half at the front there, so that's plus that one, isn't it? So that'll be plus a half log x squared plus 2. Then the last one here, we would put the 4 over this side, and again it's like arctan, where a would be root 2, so we'll have the 4 at the front times by 1 over a, and we said a would be root 2, and then arctan x over root 2 plus c. So that really is our sort of final answer. Probably a little tidy up at the end if there's things that we can put together. So the x remains on its own. These log terms, so basically have the log of this divided by the log of this, so we'll put our half at the front, and then it'll be the log of our second one, which was the x squared plus 2 divided by x squared plus 3, so that's these two terms put together, that divided by that, and then our arctan terms, well, we can't really put them together, we can probably just simplify what's out the front here. I'll do these on my calculator. So if I work out 9 divided by root 3, so that's minus 3 root 3 arctan x over root 3, and then the last one plus 4 divided by root 2, which is 2 root 2, so plus 2 root 2 arctan x over root 2, and just enough space there to squeeze in my plus c. So here we go, as our final simplified answer there. Quite a lot to do, particularly with the partial fractions. Not straightforward with the partial fractions, that first bit. Okay, you should now be able to do exercise 3D on pages 72 to 73. So when we're dealing with these partial fractions, just watch out for improper fractions, that you do your long division or equating coefficients first. Also watch out for quadratics, something like that, in the, actually let me write down quadratics in the numerator. So quadratics in the, not the numerator, in the denominator. Watch out for those, because if you have a quadratic down here, well, this is when you're doing partial fractions, then it means that you need to have something like ax plus b. So don't forget that. Yeah, it could be an x term lurking, hiding there, that we could forget about. You'll notice this arctan comes up a lot because we've got 1 over x squared plus a squared, and you're probably getting used to working out what that is actually without even referring to the formula book. So once you've actually finished this exercise, you could then go on and do the mixed exercise, because that's this chapter finished, and you'll find that on page 74 to 76. So mixed exercise, pages 74 to 76.